Okay folks, so you need to know about your gas laws. The gas laws relate four things that you can measure about a gas. Pressure, volume and temperature. The first gas law is called Boyle's law. He was an Irish guy, and Boyle's law discovered the relationship between pressure and the volume of the gas. And in this law, you have to fix the temperature. So when you're talking about Boyle's law, the temperature is always fixed, and you also have to fix the number of gas particles you're talking about. The experiment Boyle did is he plotted a graph of 1 over volume against pressure, and he realised it was a straight line graph. If you get a straight line graph, you're allowed to say P is proportional to 1 over V, so therefore you can say P is equal to some constant, which I've just called K1, times 1 over V. You can rearrange that for PV equals that constant, or you can say, well, the pressure of the gas multiplied by the volume of the gas is equal to some other pressure times some other volume, provided you're talking about the same amount of gas at the same temperature. Charles done a similar thing. Charles was interested in what happened when he varied the temperature of the gas to the volume. Charles had to do this at a constant pressure, also a constant number of particles. When Charles done this experiment, he got this nice straight line. He realised if he extrapolated back, it intersected the axis, the temperature axis at -273. How does a gas exert zero volume? The particles can't be moving. Since we know temperature is associated with how fast the particles are moving, if the particles have stopped, that must be the lowest possible temperature. So that's how we know absolute zero is -273. Normally when we plot, we don't plot degrees Celsius on this axis, we plot Kelvin on this axis. And when you do that, that means the graph starts at zero temperature and it goes up. Obviously, if you've got this graph, you can say volume is proportional to temperature. Therefore, you can say volume is equal to some constant, which here I've called K2 because it's a different constant to this, times temperature. Therefore, you can rearrange it as volume over temperature is equal to K2. And then you can do just the same thing that we done with Boyle's law. Compare two scenarios. So this is an earlier scenario, this is a later scenario. They must be both equal to the same constant. The pressure law is very, very similar again. This time we keep the volume constant and the number of particles constant, and we get this graph here. Again, if you extrapolate back, you'll find that it cuts the x-axis, or the temperature axis, at -273. How does the gas exert zero pressure? It has to not be moving, it can't be colliding with the walls. So you can rewrite this graph with Kelvin on this axis, and therefore, because you've got this straight line, just like here, you can say the pressure is proportional to the temperature. Therefore, pressure is equal to some constant K3 times the temperature. And then you can say, well, it's the same as what we've done here. You can say P2 over T1 equals P1 over T1 equals P2 over T2. And that is the pressure law. So both of these came up with the same value for absolute zero. Importantly, with both of these two laws, you only get the straight line graph through the origin when temperature is measured in Kelvin. So if you're using this law or this law, you must have the temperature in Kelvin. You'll get away with it in this one here. So that's why, if you want a master equation to help you remember all these, and this is the best equation, it's this equation here. How much sense does that make, Will?
A good amount.
Do you get it?
Yeah.
Okay, stop that one there.